And now let's continue with Jan Yurdanov and his presentation.
So today I will talk about quantum communication and quantum internet, its applications and challenges for building a global quantum network. Now, building a global quantum network is a challenge that combines a variety of new methods and existing technologies to achieve the required reliability and scalability in communication system. It can be utilized in space agencies, science tech institutions, telecommunications companies, governments, financial institutions, and healthcare providers. Uh, Even today, quantum computers are not so well developed and cannot do so much to encrypt our systems. Uh, Tomorrow, we can see the IBM roadmap, for example, in 10 years, they will have ability to decrypt even the most well-protected data in a relatively short time. So the method collect now and decrypt later becomes a real threat since sensitive data which can be stolen today uh, will be encrypted tomorrow and then when quantum computers are sufficiently developed. So this is a problem that stands today, and quick resolutions are needed to protect today's data for such a method. But let's see for now. Okay, how we can use such new technology because it can play a key role in the space system, secure communication, information processing, navigation, and science of the future. Maybe the first technology that will take place is quantum key distribution. Actually, a lot of investments are done in this area because to protect our data today. This is the next step in security evolution, which will open new horizons in building and expand global quantum network. Because unique properties of the quantum mechanics principles, such as superposition, entanglement, and teleportation, allow us not only to generate and distribute secure quantum keys, but also to transfer quantum information between quantum devices. So increased investment in this field led to a new technological breakthrough in the propagation of quantum keys over vast distances via terrestrial infrastructure with current existing optical fibers, but also with intersatellite and satellite-to-ground quantum communication. Such innovations enables the interconnection of future quantum sensors and quantum computers and becomes a key to making the global quantum network a reality. We mentioned already future applications like quantum key distribution. It is to establish a key for secure communication. Actually, today, the first quantum links are being used to demonstrate quantum application in cybersecurity and metrology. Even before a mature quantum internet exists, the development path promises many near-term applications, making both the journey and the end goal worth the investment. But also, there are a lot of other technologies that will take place when you have such advanced communication network. This is distributed and delegated quantum computing. Uh, Maybe the future of quantum computer is not to have a personal quantum computer in our room, but to use a super quantum computers remotely uh, for complex calculations. We can take a time for this. But also to have interconnection between multiple quantum computers, so to increase their computational power. Another feature is distributed quantum sensing and quantum metrology. based on unique quantum effects, we obtain sensitivity that are not possible to achieve classically. Satellites will enable unique test of quantum entanglement. Extremely sensitive interferometers are providing valuable insights into our universe through measurements of gravitational wave, for example. We can remember this stunning picture of a black hole captured in 2017, I believe. It was made by multiple connected and synchronized sensors on ground-based, like a big telescope, big like the Earth. So yeah, combining a multiple sensor will increase their sensitivity and accuracy. But let's talk about quantum information. We already hear today some of the benefits of bits instead of qubits instead of bits. One of those is possibility for superposition. We can have state 1, state 0, but both states in the same time. Such quantum system actually has probability operators A and B. Those coefficients actually denote the probability of measuring either 0 or 1. But the superposition principle lies in the base of quantum entanglement, where two or more qubits can be entangled in one system with a common A and alpha and beta coefficients of the wave function. For example, quantum system with two entangled qubits can have the following wave function. This is one of the possible entangled wave functions. We can see that we have probability only for both qubits to be 0 or both qubits to be 1. There is no probability for example, 0, 1 or 1, 0, which means that they are synchronized and they will always be with the same measured value if we try to measure them both. This is one example of Bell state. There are other. So measuring the state of quantum system does not follow the same intuition as measuring the classical one. And actually the act of measurement itself leads to collapse of the wave function. And the qubit takes a state of 0 or 1, depends on its coefficients. Further measurements will not give us more information about the quantum state because actually we lose the quantum information because of the collapse of the wave function. And same is applied for entangled qubits. They share the common wave function and common coefficients. So measuring the first qubit defines the state of the other with no matter of the distance. Actually, we can entangle more than 2, 3, 5, and more. And they all are connected in one wave function, and they have one probability coefficient. One or more, in this case, if there are more. But we are only allowed to make just one measurement. And even in one basis, we can measure, for example, for state of the qubit, computational state 1 or 0, or phase of the qubit, plus and minus. We will see those properties on the next QBulgaria and QSlovenia elections. But this is one and unique properties of quantum information, that there is no such analog in classical and deterministic systems. So to complete quantum information, the complete quantum information cannot be extracted by measurement, and therefore cannot be reconstructed and copied. This is the key in the no cloning theorem. So the probabilistic nature and uncertainty in the measurement of quantum systems is a key instrument in quantum cryptography, as it prevents quantum information from being copied, which prevents from being eavesdropped. And quantum entanglement is an important resource in quantum communication as it allows the implementation of other algorithms like quantum teleportation and entanglement swapping. But why we need quantum communication? We already exchange terabits of classical data through our terrestrial and space classical communication infrastructure. It's because there are new game-changing technologies gaining momentum now in front of us, such as quantum computing, quantum key distribution, and quantum sensing and metrology. They all are quantum, and the industry players claims groundbreaking progress for the next 10 to 20 years. Let's move back to quantum communication. It's based on the main carriers are qubits. Usually, they are microscopic objects such as electrons, photons, or atoms. Their properties are difficult to extract from macroscopic objects. But for example, the polarization of the photon is a physical property that can be that carry quantum information, and the process of encoding, manipulating, sending, and measuring is actually relatively easy to be implemented. We also send the photon over relatively large distances while preserving its decoherence. Actually, preserving its coherence. We save it from decoherence, which makes it convenient as a physical carrier for quantum communication. We can use even our existing fiber network for this by using photons. The principle of quantum mechanics usually offers unique and novel features, but also lead to some specific limitations that are a real challenge for the implementation of quantum communication network with the necessary scalability. One of them is the limitations that we are not possible to copy quantum information because of the no cloning theorem. This is a serious problem because it does not allow us to build error corrections like in usual classical system. We use repetition codes, but repetition codes need a copy of the information and transmit it multiple times. We cannot copy the information. We also cannot amplify or retransmit the signal that is attenuated due to the length of the path in the way how we do it in the classical systems. So we need quantum repeaters, which are completely different than the usual one. Eh, So we need new quantum systems and technologies which are compatible with the quantum specifics. So entanglement can be used for quantum error correction. There is a very famous algorithm, Shor's algorithm for quantum error correction, which use entanglement and unified and unitary operations for saving the quantum state and restoring the quantum state. But actually, for one qubit, we need at least another 8 qubits to be able to restore the error. And a lot of unitary operations, those are actually quantum gates. They also have errors. So error correction is a hard task. But anyway, there are possible ways to mitigate the error corrections, to reduce it, and to work with it. Another feature is quantum teleportation. It's again based on entanglement. It is used for transferring the quantum information over extremely long distances, but also to build secure information bridges between local terrestrial quantum networks. Maybe next week we will know more about quantum teleportation as an algorithm. The important here is that we need quantum channel to send entangled to separate the entangled pair, but to teleport the quantum state from Alice to Bob, we need also classical communication channel. So it cannot happen just like that. Uh, and there are some limitations on it. So another application of entanglement and uh, teleportation is very important today because it allows us to build a global quantum network by possibility to implement quantum repeaters. They are different from the usual classical repeaters. This is done with quantum algorithm entanglement swapping, which is based on teleportation algorithm, but we have some intermediate link Charlie in the middle, which actually plays a role as a repeater. This is like teleportation, but on already entangled particles. And this algorithm actually can be used repeatedly by multiplying the distances, just like the classical repeaters, as long as we have successful delivery of entangled pairs between quantum nodes and an acceptable error rate when performing quantum operations in them. Because there is a price. Each repetition algorithm actually includes other errors, and at some point we cannot restore anymore the quantum information. And we go to space quantum communication. Why space? Because the space-based quantum communication actually already show us more than 100 and 1,200 kilometers entanglement distribution. This was done by a Chinese quantum satellite Mikyus. A lot of satellites are now in space for such experiments and keep going. But this mission goal is not only quantum key distribution and practical quantum communication in space, but also to conduct fundamental tests in quantum mechanics, quantum entanglement, and quantum communication on a global scale. The basic principle for such communication is that it is optical, implemented with lasers, satellites, and telescopes. Polarization is used, is the most suitable coding method for free space and entangling pairs exchange in the main instrument. Uh, Now is the moment to say that there are other encoding methods, not only polarization and entanglement. They are phase-based, time-based uh, types. But for space communication, the polarization is the most suitable one because of the noises. It's handle those noises. We can say that there are some different configurations for implementing ground-to-satellite communication, each with its own advantages and disadvantages. But why space quantum communication? We already have our fiber optics, our existing fiber network, of, through which we can send quantum information. It is actually the current practice. It is used for quantum key distribution, but unfortunately for the short distances, because optical ground channel link loss increases proportionally through distance. It's about 0.2, 0.3 decibel per kilometers. And at the end, it needs quantum repeater on each 100 and 150 kilometer. It's not a problem. We can build a quantum repeater. Let's say in the future, we can build error corrected quantum repeaters. But such nodes on each 100 kilometers, they should be trusted nodes. And if we want to implement, for example, quantum key distribution on longer distances, all those nodes need to be carefully secured, which is kind of complicated and weak point. In the same time, with the free space channel, it is communication with satellites. The losses increased logarithmically through the distance. So it can reach more than 500 till 1,200 kilometers, including the atmosphere and beam spreading. So it's suitable for usage of quantum repeater of long distances. There are several way for several architecture for entanglement distribution. Uh, let's talk about three of them. Duo downlink, in which the entanglement is prepared on board on the satellite and sent to the ground stations. It's not require synchronization between the ground terminals and the satellites. It's very actually one of the useful way, but yeah, the complicates technology complicates is because entanglement pairs need to be created on the satellite itself. The other variant is dual uplink, on which entanglement is generated at each ground station, and photons are transmitted to the satellite. The satellite performs a Bell state measurement and relays the outcome back to the ground station through entanglement swapping. The ground terminals now share the entangled state, but this approach requires that the photons are arriving at the same time to the satellite. And you can imagine how complicated is this. The satellites are moving, fast-moving objects and need to be carefully tracked from the ground stations. And because of this, there are some relative effects because of the moving distances between satellites and ground station that need to be compensated. So this synchronization is a real challenge. But it's experiment. There are such experiments. They are successful, even hard, but successful. The third way is hybrid approach, where one ground terminal transmit the photons to the satellite, and the satellite acts like a passive routing device to retransmit the photon on the second ground station. Again, we don't need we don't need synchronization between the satellite and the ground stations. Probably synchronization between the ground stations are needed in this case. It's important here to say that such algorithm actually in such algorithm, the data, the information has nothing to do with the satellites. The ground station exchange the information. For example, dual downlink. Our satellite just sent entanglement pair to the ground stations. And ground stations use this entanglement for entanglement swapping or for quantum teleportation. And the information that they exchange has nothing to do with the satellite. It's pretty secure. It uses this quantum bridge between the space and time, and the only weak points are actually the ground stations. Okay. About the challenges, actually there are a lot. But there are a lot of investments. So with investments, so next years we will see the result of this. So the main challenge in quantum systems is decoherence. In space quantum system, this is cosmic radiation and other environmental factors that can disturb quantum states and to reduce the reliability of communication. In fiber optics, this is the specific of the fiber optics itself. They cannot use polarization. They use other type of encoding. But anyway, there is a problem with decoherence because actually we need to save our qubit, our tiny photon, to not interact with anything around it. So to save it quantum state. And this is very, very hard. The other is technological barriers. To develop quantum repeaters, satellites, and ground stations require significant advancements in quantum technology, such as high-resolution clocks, precise tracking systems, single photons emitters and receivers, quantum transducers, and quantum memory. Yeah, two words about quantum transducers. Yeah, if you want to create a hybrid quantum network, which include satellite links, terrestrial links, If you want to connect quantum computers, then we need tools that can, devices that can change the that can transfer the quantum information from another physical system, from one physical system to another physical systems. For example, quantum computers use superconducting conducting points as a qubits. Communication uses the photons. So the quantum transducer is a device that can transfer the quantum information from superconducting dot point to uh, quantum dot to photon polarization, for example. The other is distance limitations because maintaining entanglement over interstellar distances remains really challenged. Also, when we talk about space communication, when we talk about communication through satellites, this is something that can be done only uh, during the night and in very good weather condition. So there are also such limitations. Of course, since infrastructure and cost, building and launching quantum satellites is expensive, and establishing a global network requires international collaboration. And last but not least, standardization and regulation. This is a completely new technologies that are mainly in labs and in the universities. They are still not well understood, let's say. So it's hard, more or less, it's hard to create basic standards and regulations for such a technology. Thank you. Thank you for your attention. And if there are some questions, see the chat.
Thank you very much, Yanchu, for your presentation. It was really, really interesting and also very detailed. As I see for now, there aren't any questions. So I also want to invite the participants again to be active in the server. So there they might open the discussion to ask questions, to give opinions, everything. So let's finish today. I saw there was a question about the homeworks. Every one of you has received a Canvas account via email. So try to connect and to see there all the tasks that you have to complete during the course. You have enough time for that, but just enter in your profile there and check everything that is in front of you. And of course, if you have questions, ask in the Discord server. Thank you very much to QSylvania about the great presentation, and of course to Dr. Chetri, who explained so many things today on the motion. Yeah, Alyosha,
Yes, yes, thank you very much.
thank you very
It was
much.
a pleasure. Yeah, so we'll see each other next week, no?
Yes, we're going to see each other again the next week, the same time.
Fine.
Bye. See you.
Bye bye.
Bye.